Adsorption is a process that as you can see, is like shown here in this figure, is a process that we have. Okay, first of all, I put a video YouTube link for you here, so you can have a look at it, and it will help you to understand this process. So we have a wet gas, natural gas. We have lean glycol, is a fresh glycol coming from top, wet gas from bottom. So this move up, liquid, the glycol moves from top to the bottom, so they will be in contact. We can use a tray, it's like a distillation column. We can use tray stage, so they will be in contact on the stage and separation will happen. And at the end, at the top, you have your gas, natural gas, free of water or kind of clean gas. And at the bottom, you will have rich glycol that goes to several steps, and it will be regenerated in another column that we call it a still column. It's like a distillation column. So what will happen? We have a reboiler, we have a condenser at this column. So glycol will be introduced, rich glycol, which has a lot of water, will be introduced to this column, and then glycol that has water will be separated from water in this distillation column, and at the end we collect our water at the top, and our lean glycol, which is a clean glycol, fresh glycol free of water, goes all the way back to the glycol contactor column. Okay, so I'm gonna talk a little bit about this part here, and this reboiler, the operating condition of this steel column. So those are the main components that we need to consider when we are designing this process. So this column, the glycol contactor, is an important piece of equipment that we need to adjust the operating condition, let's say pressure and temperature. For the reboiler, the heat duty of the reboiler is also an important parameter that we need to again adjust the temperature of pressure of reboiler to make sure that we have a efficient process. And also the distillation column, the operating condition of distillation column, temperature and pressure, is also important design parameter. Next, okay. So we have a inlet gas, which is a wet gas that goes inside the column. So it's similar to acid gas treatment. We have a separator that can separate some impurity from the gas. So first of all, if the inlet gas, let's say, is coming from another unit, okay, if it has a higher temperature, the higher temperature means higher humidity. Most of the time, higher temperature means higher humidity, because when we have higher temperature, the water can vaporize and goes to the gas way. So if you have a higher temperature in this inlet gas, we will have more water or higher humidity in this inlet gas. This is the first point. So if we have higher temperature in this inlet gas, higher temperature means my glycol in this column has to remove more water because it has more water content, and so it means more job for us. We need a bigger column, we need more stage, or we need more circulation of glycol to reach to a specification which is needed, the pipeline specification. This is the standard, this is the maximum or kind of a standard amount of water that we need to have in our pipeline, which is 7 pounds of water per each million metric cubic foot of natural gas. Okay, so we have to always remove water to reach to this standard, which is 7 pounds of water in each million metric cubic foot of natural gas. So if you have higher inlet temperature in the inlet gas, it means we have more water content, and we need to have a bigger device, or we have a bigger job to do. Okay, and also an increase in the gas temperature can also increase the gas velocity. Why? Let's look at ideal gas equation. PV equal to nRT, right? So if we have volumetric flow rate here, we have we have a mole flow rate here. So like we can have this relation. If we can also convert this to mass flow rate divided by molecular weight, right? Sorry. Again, it's not corona, don't worry, it's just allergy. Now, if I increase the temperature here, alright, so what I will have higher volumetric flow rate, right? If temperature is higher in the inlet gas, volumetric flow rate is higher. Volumetric flow rate is velocity times area, right? So if I have volumetric flow rate, the velocity will also increase, okay? So it means I have higher velocity, so if to avoid any kind of flooding or anything, I have to what I have to do, so if my velocity will increase, to keep the velocity constant, I have to increase the water, the area or the column diameter, all right? So when I have higher temperature, volumetric flow rate will increase, so it means it will lead to increase in velocity. If I want to keep the velocity constant, unchanged, I have to increase the area, or it means I have to increase the diameter of column, which is more expensive, more maintenance, and more work to be done. Okay, so some consideration about the design of this process. Okay, we can have different type of glycol. Glycol is the alcohol. It's the type of alcohol that it depends to the number of oxygen or alcohol units connected together. I mean, like the specification, I mean, the type of alcohol, it really depends to this oxygen group. Like we have 3-ethylene glycol, which has this type of structure. We have tetraethylene glycol, which has this type of structure. So each of them, they have their own specification and properties, and using them really depends to the type of the process we are dealing with. Then, okay, if the gas inlet temperature is too high, is above 120, okay, we can have a big loss of glycol. However, if you have a high temperature, we can replace 3-ethylene glycol with tetraethylene glycol. Tetraethylene glycol, since it's a bigger molecule, it has a higher boiling temperature, So this high boiling temperature means we can operate at higher temperature without boiling or vaporizing the glycol and losing it. Okay, but usually it is common to cool down the inlet gas to below 120, especially if you are using 3-ethylene glycol, to avoid losing any glycol. Okay, so by having a temperature a little bit below 120, we will avoid losing the glycol. And also we have to always stay above the hydration formation temperature. Hydration formation temperature is like a low temperature that we will have hydrates. We will have some of our water that goes to gas, or either to the liquid, or either even solid phase. So we have to be careful to stay a little bit below this temperature, but not too much below this temperature to avoid the formation of hydrate. So the minimum inlet gas temperature is normally above the hydration formation temperature and is always above 150 Fahrenheit. So 50 Fahrenheit is a temperature that we can have the hydrate formation. So we have to work above this temperature and below this temperature for our inlet gas. Below this 50 Fahrenheit, we will have, there is a high chance of formation of hydrate, and at the same time, the glycol, which is a viscous, which is a liquid, will become very viscous. Okay, very viscous means lower mass transfer efficiency, higher pumping needs, and pumping power, and some other issues. Below another problem, like at temperatures, at low temperature, like temperatures 60 to 70, is that the glycol can form a stable emulsion with the liquid hydrocarbon that can also cause some foaming issues. So as you see, we don't have a big flexibility in general to operate at any temperature that we want. So below certain temperature we will have some issues, above some certain temperatures we have some other issues. So we have to always adjust the temperature carefully. For example, in case of using triethylene glycol, typically the gas temperature, the inlet gas temperature, is something between 80 to 110 by considering all the above mentioned points. So this slide is important. As you see, like there are a lot of important information in this slide that you need to kind of learn them carefully. Okay, the contactor pressure, operating pressure, is also another parameter that need to be considered, but comparing with temperature, operating pressure doesn't have that much effect. Okay, as long as we are below 3000 psi, which is a high temperature, which is almost 200 bars, we are okay. We won't have any big issue. But in general, if we increase the pressure, okay, if we increase the pressure, is most of the time is good, because when you have higher pressure, you can condense, or you can force the water vapor to go to the liquid phase, right? So you will have kind of more condensation, or more transfer of vapor of water to the liquid phase, which is good for us. So working at high temperature can lead to a better absorption. So for absorption, we know that always low temperature is good, and low temperature and high pressure. But as I said, we cannot play with this temperature that much, as I already explained in the previous slides. So there is always a certain range for both parameters. So when we have a smaller contactor, we can go at even higher pressure, very high pressure, so because we can manipulate it easier, especially if the gas velocity is low. So we can, small contactors that usually have lower velocity, so we can go to upper pressures, higher pressures, to increase the absorption, and we can increase the capacity, as absorption capacity as well. Okay. If we are working at higher pressure, so we need a stronger column, we need a stronger wall, a stronger body of the column. So it means we need a thicker column. But if we are working at low pressure, we can use even less wall thickness. Okay, that less wall thickness means less capital cost, less material to be used, less expense, right? So that's good, but in general, the dehydration pressure is between 500 to 1200 psi. This is a typical temperature that used in dehydration. Okay, number of stages. As I said, this column is like a distillation column. The glycol column is a distillation column that has different stages, that has several stages. These stages are not equilibrium, although when we are going to design it, we will use those kind of equilibrium curve. Okay, so as I said, we need to decrease it. We need to decrease it to okay. As I said, we will use McCabe column, McCabe curve. Sorry, like McCabe curve, or if you see in Unit 6, we are using equilibrium line and operating line. Then we will talk about equilibrium stage, but none of this stage can reach to equilibrium. And the efficiency of these stages, especially in the dehydration process by glycol, is very low. It's only 25%. It means each stage only does the job of 20% of the job that it's supposed to do. And actually each four stage can do one equilibrium job. I mean, each four stage can do a job of one equilibrium stage. If the stage was equilibrium, so it means we needed less tray or actual tray. So for the bubble cap, this is a bubble cap. You know what's the difference between bubble cap, sieve tray, and valve tray. You already know it in Unit 5. So the normal spacing between the tray is 24 inch. It means the space between these two trays, the upper one and lower one. That, as I said, we use this stage. We use this distance, this height, to make sure that we use this height to make sure that in case if we need to do some maintenance, we need to do some repairing, so we will have enough space to do that, to go inside the column sometimes and do the repairing. Okay. The more tray, the greater the dew point depression, okay, and less fuel or heat duty for the reboiler. Okay, I will explain this a little bit here. Okay, so if you have more tray, if we will have more tray, okay, we will separate more water from my glycol. This glycol at the end, it will goes to the reboiler. Okay, it will be sent to the reboiler. So the glycol, okay, let's say, okay, it will be sent to the reboiler. If we have less water in this glycol, in the reboiler we need less energy to vaporize this water, because water has a high energy capacity, heat capacity. So if once we send this glycol that contain water, because it's absorbing water from our natural gas, and then we will have to send it to reboiler to remove water, regenerate the glycol, send it back to this column. Okay, so when we send it to reboiler, it has a big amount of water that we will boil it to remove this water. So if we have less water, it means we need less heat duty in the reboiler. All right. So it means, what does this sentence mean? It means if we have more stages in the glycol column, in this absorption column, so we will remove more water. So we can in the regeneration we can save some energy. All right, so this is this is in the regeneration process. We can save some more energy. So this is about the glycol column, and then okay. So, but adding more tray comes with some expenses, some maintenance expenses, construction expenses, and some other issues. So there is always should be a compromise between all these parameters when we design the column. So if you increase one parameter, you will affect some other parameters. So like at the end, as I said, designing all these parameters together has to be done by considering the advantage and disadvantage of each of them. That for now we don't need to go to more details. If you really need more information, I can introduce you some references. Okay, as I said, most of the contactors, the absorption columns, they are designed to have at the end, when I have my natural gas that goes out of this column, the natural gas that goes out of this column, I want to have maximum 7 pounds of water per each million metric square foot of natural gas. That usually between 6 to 8 trays is enough to do this separation for us. Next, okay, we are going to talk a little bit about the lean glycol temperature. So this is my glycol column that I have at the bottom. I will collect glycol, I will send it to the distillation column with reboiler, condenser, everything, and I will remove water, and I will make a fresh glycol or lean glycol and use it back again in the column. We have a heat exchanger here. I already talked about the function of this heat exchanger in unit 6, and even in unit 6, why that we have similar heat exchanger in our acid gas treating by using solvents like amine groups. So you know that we use this heat exchanger to remove some of the heat from the glycol, because we want to use this lean glycol in the absorption process, that we prefer to have lower temperature. So we prefer to keep the temperature here low. But as I said, we cannot have very, very low temperature because we can condense some hydrocarbon, and there are some issues. Glycol becomes very viscous. Those are the issues that we can face. So this the temperature of this lean glycol can have effect on dew point depression. So what is dew point depression? We are talking about natural gas that is wet. Natural gas dew point is kind similar to like boiling point, right? It's the point that when you condense a gas, you will see the first droplet of liquid. So natural gas has a dew point, let's say, this is not an exact number, I'm just giving you some idea, has a dew point of minus 100 degrees C. It means natural gas in minus 100 degrees C, it will be condensed. Water will be condensed, let's say at which temperature water will be condensed. Let's say if you are talking about one atmosphere, the condensation will happen, water will be condensed in let's say in 1 atmosphere. I don't remember the exact number, but is, let's say, I don't know, like 10 degrees C, something like that. I have to look at the table and see what's the temperature, the saturation temperature of water at 1 atmosphere, but just let's say 10 degrees C. So your wet natural gas has both natural gas and water, right? They are combined together. that the dew point is something between these two, okay? But something between these two, let's say, is minus 80, okay? If we have depression, means decrease in the dew point. If I have lower dew point, for me is better, because like lower dew point or more dew point depression is better for me, because it means I will have less water content, okay? Less water content, that is easier to remove, so I will need less glycol or less glycol circulation to remove that water. All right, so this is it's kind of more explanation about this dew point depression. So if so the inlet glycol, the lean glycol temperature is important, because it can, when we have low temperature here at the inlet, we can have more water to be absorbed. When we have more water that will be absorbed, that goes to the glycol, it means we will have a better dew point depression. It means we will have, my natural gas will be pure, will be more free of water, so the dew point temperature will be lower, or it will have more depression in the dew point. Then okay, the higher the lean glycol temperature, it means the temperature here, the higher temperature here, it means the higher loss of glycol exiting the contactor with the dry gas. So like if you have higher temperature here, so your glycol will be vaporized more, so you will lose more glycol. The glycol will go to the gas phase, the dry gas that is leaving your column here. So we have to adjust this lean glycol temperature inlet, which is because it affects a lot of things. And also, as I said, we cannot bring this temperature too low. We cannot make it too low, okay? Because if we make it too low, we can condense some of this hydrocarbon, some of the natural gas. We can condense it, and we will send it to the glycol phase that we don't want it. We don't want to have this natural gas who goes to the glycol phase. We want only the water goes to this glycol. So in the most design, the glycol temperature is a little bit above the gas that is leaving. So in most of the design, the glycol that is entering here is 10 degrees Fahrenheit warmer than this gas that is leaving, to avoid the condensation of this gas. Okay, glycol concentration. So the glycol that we use, okay, can come with different purities. So the higher concentration is better because it's more pure. The higher concentration of the glycol, it is more pure. It can absorb more water because the mass transfer mass transfer will be much better. The thermodynamic tendency, the thermodynamic, the attraction of the water to the glycol will be better. It will absorb more water, so we will have a better dew point depression. As I already explained in the previous slide, what is dew point depression? So it means we need less glycol circulation rate, or less glycol in general to be used and less number of tray to do the same separation. So if we have a more pure glycol, it means I will have more dew point depression, for a given glycol circulation and number of tray. Or it means if, let's say, we in general, for the same job that we have to do, we need more glycol circulation, more glycol circulation, less glycol circulation rate, or less number of tray because it's pure, and the concentration between 98 or to 99, that's the kind of common concentration of glycol that is used in those kind of dehydration units. Okay, another important piece of equipment in this process is the reboiler here. So what I have my rich glycol will be introduced, rich glycol that has a big amount of water. It will be introduced to this distillation column that I have, like any normal distillation column. I have condenser and reboiler. So then this water will be removed from this glycol. Water will be collected at the top, either as a vapor, water vapor, or liquid water. I mean, water, like in the liquid phase. And then I have glycol that here I will, at the bottom, I will have more glycol to be, to just, for your information, glycol has a higher boiling point. The boiling point of glycol is higher than water. That's why glycol will be collected mainly at the bottom of distillation column, that we have reboiler, and water will be collected here. So here in the reboiler, I will use a reboiler here to boil the liquid coming here, which is rich in that has mainly glycol. So I will remove my pure, lean glycol, which is rich glycol. It has only glycol, is lean, is poor in water or rich in glycol, and then we send it. This will be sent to the absorption column. So this reboiler, the operation of this reboiler, the operating temperature, pressure is very important because the temperature of this reboiler can control the concentration of water in the lean glycol. So this lean glycol is although very pure in glycol, but it still has some water. It's not 100% glycol. It has some water. So because we cannot completely separate water and glycol in distillation column. So this water vapor here and liquid phase, they have some glycol, a little bit amount of glycol, and this glycol here has a little bit of water. So the reboiler temperature can affect the concentration of this lean water in this lean glycol. The higher the temperature, the higher the concentration of glycol. Why? As I said, glycol has higher boiling temperature than water. So in the reboiler, if I increase the temperature here, more water will leave the glycol and goes to the top of the column. So if I increase the temperature here, I can have a more pure glycol here that has less water, because if I increase the temperature, since the boiling temperature of water is less than glycol, more water will be leaving the glycol and it will go to the vapor phase and leave at the top, and I have a more pure glycol at the bottom. But the temperature between 370 to 390 Fahrenheit is a kind of a typical reboiler temperature in such a column. And in this temperature, we can reach to a glycol concentration of 98.5 to 98.9%. It means the concentration of glycol here in this part. Then we have reboiler pressure is also, it can has also some effect. Pressure above atmospheric can significantly reduce lean glycol concentration and dehydration efficiency. So this makes sense Okay, this makes sense, because here, if I increase the pressure in the reboiler, what I will do, I will make the escaping of water more difficult. If I increase the pressure here, the water prefer to stay in the liquid phase to come to the gas phase, because the pressure is high. So what will happen at the end, in the exit here, in this lean glycol, I will have more water, because I increased the pressure and I didn't let the water to go to the vapor phase and leaves from top. I force the water to stay in the liquid, so that's why I will have more water here, or less concentration. So less concentration of glycol means lower efficiency of this dehydration process here. So what we have to do in this column to avoid this kind of problem, we have to vent it. We have to make sure that we don't have the high pressure here, or in general in the column, so we can use some venting system. And also another issue is that let's say if in this column, this distillation column, that sometimes can be a packed bed, we use packing. So this packing, if they are if they are blocked by some impurities, by some solid particles, so they can produce a big pressure drop. So big pressure drop means we will increase the pressure at the top. So if we have a obstacle in front of the gas phase, so the pressure can increase here at the bottom. So if we have a high of the pressure drop, so it means we will have high pressure at the bottom. So this high pressure is not good. So we have to replace this packing more often to make sure that we won't have any excess back pressure or pressure drop. So we can also work at temperature below atmospheric. Below atmospheric, it means we have to create vacuum. All right. So if we decrease the pressure here by creating vacuum, so we can decrease the boiling point. Decreasing boiling point mean we need less heat duty for reboiler at lower pressure, because the boiling temperature will decrease, but it has also some issues. So we can work at below atmospheric temperature, that we will decrease the boiling temperature. It means we will have less heat duty of the reboiler, or we can reach to a higher concentration here. But creating vacuum, first of all, is an issue, because you need a specific design to create vacuum, and it makes the process more complex. And also when you have vacuum, you can also create some when you have vacuum, you can also increase the air leak to the system. Air leak to the system leads to the degradation of glycol, which is not for us. So instead of decreasing the pressure, sometimes we can use a stripping gas. In the reboiler, we can use the stripping gas inside the reboiler. So this stripping gas sometimes can be the vapor itself, saturated vapor. It can be some other inert gas. So this stripping gas can remove some of the water for us, which is easier. So instead of using lower pressure, that is problematic, we can use the stripping gas in the column, in the reboiler. I have a photo that shows you how we use this stripping gas in the reboiler. I can show you in the next slide. However, if we really need a pure glycol, it means pure means 99.5, something like that. So sometimes we can work in vacuum. Which vacuum? Vacuum this pressure, 500 millimeter mercury absolute pressure, or 10 psi absolute pressure. We know that atmospheric pressure is how much? Atmospheric pressure is is 14.7 psi. So working at lower than 14.7 psi means vacuum or below atmospheric pressure. Okay. Next, about using the stripping gas. So when we have a stripping gas, our reboiler configuration will be like this. So this is my reboiler. Then I can send the liquid from my reboiler. I can send the liquid to reboiler to a kind of a stripping vessel. So in the stripping vessel, I use a stripping gas. So this stripping gas goes to the liquid and it can absorb some of the water, and then we will send this stripping gas all the way to the column, and we will collect it from top of the column, and at the bottom you will have a more pure glycol that goes to the absorption column. So this stripping gas, if once we use a stripping gas, we need another vessel, something like a surge tank, to do the job for us. So when okay, the stripping gas can be a wet gas. Okay, it can be a wet gas, either maybe natural gas or that is saturated with water. Okay, it's a stripping, although it's saturated, but at this temperature it can absorb some more water vapor. And a stripping gas can have a very high capacity, something like 100,000 pounds per each cubic million metric cubic foot of natural gas, and at high temperature of reboiler, 370 to 390 Fahrenheit. So the stripping gas can really increase the concentration of glycol to something like 98.5 to 98.9. Okay, glycol circulation rate, it means the flow rate of the glycol in the process, especially in the absorption column. So if let's say we have the number of trays is fixed and the lean glycol concentration is also fixed, we cannot play with these two parameters. These two parameters, both the concentration, number of trays, can affect our separation, dehydration capacity, right? So if these two are fixed, another parameter that we can play with is the glycol circulation rate. Circulation means the flow rate of the glycol that is moving inside the two columns, inside the absorption and the regeneration column. Okay, so in general, the more glycol that comes to the contact with the gas, we will have more separation, more water vapor that will be removed from the gas. Okay, more circulation rate means more separation of water from my gas. But there is always a minimum maximum range. So minimum amount of circulation rate is 2 gallons of glycol for each pound of water that we want to remove. So the minimum for each pound of water that we want to remove, we need at least 2 gallons of glycol. And there is also, of course, a maximum for that. Maximum is 7 gallons per 7 gallons per pound of water to be removed. Okay, so maximum is 7, minimum is 2. The common design is 3 gallon per pound. Okay, common design is 3 gallon per each pound of water to be removed. So the minimum is 2 gallon per each pound of water to be removed, and maximum is 7. Okay, minimum 2, maximum 7. 3 is something optimized that will be used most of the time. 3 gallons per each pound of water to be removed. Okay. Glycol circulation rate. Okay, so as I said, we will have a minimum and maximum for this glycol circulation. We cannot go to below 2 and more than 7. If we go to very high circulation rate, excessive circulation rate, so it means there is more glycol that goes to the reboiler, and we can overload the reboiler. Okay, so when we overload the reboiler, the glycol regeneration will be less efficient. And also, if we send more glycol, if we increase the circulation rate, we will send more glycol to the reboiler, and we can decrease the reboiler temperature, because there is more, because usually the absorption column here, okay, we have regeneration, absorption, and regeneration. The glycol that is coming from absorption, it has lower temperature. So if we send more low temperature liquid to this column, it means in reboiler I need more heat here. In the reboiler I need more heat to be added, okay, to maintain the temperature. So if we increase the circulation rate, we can decrease the reboiler temperature if, let's say, we keep the heat duty constant. Okay, so that means when the temperature is decreased, there is less water that will be separated in the reboiler. Okay, less water will be separated in the reboiler, and we will have the concentration of glycol will decrease in the lean concentration. Okay, and the amount of water that has to be removed will also decrease. So we will have less pure glycol in this essay. So those are some photos that you don't have to really memorize them, or kind of I don't know. You don't really need to memorize them. It's just some samples of how, when we design, like there are such a curves that we will consider that in different circulation rate, what will be the amount of glycol that will be removed, and so on. System sizing. Okay, so there are some parameters that will affect the system sizing. Just 1 second here. Okay, I just need 1 second pause, because I need to check something here first, and then I will continue. Just stay. Okay. So okay, so sizing the system. Okay, sizing the system. it means we have to calculate the diameter of the column. Okay, sizing is all about the number of tray that we need. The number of tray can that will define the overall height of the column. Okay, also the rate of glycol circulation rate, the lean concentration, reboiler heat duty. Those are the important sizing parameters that we need to consider when we are designing such a system. And they are also interrelated, all right? They are also interrelated. That, as I said, if you have more tray, okay, more tray means we have more tray, more separation. Let's say it means we need less circulation rate for our glycol, or less glycol concentration, lean glycol concentration needed. So those are some design consideration. And when we are talking about design, what does it mean? Okay, like in this kind of column, it means just finding this parameters, right? I mean, calculating this parameter based on the process that we have. Okay, stripping steel temperature. So now we are talking about the distillation column that we have reboiler. Okay, as I said, we can have also we can have also, sorry, this is this way, this is this way. Okay, so this is the distillation column that we also call it a steel column. Okay, we also call this a steel column. So at the top of this column, I have my condenser that condense because here I have mainly water with little bit glycol, a small amount of glycol here, mainly water that goes here. So then we get most of the water at the outlet of this condenser, and we also condense. We use this condenser to condense some of this vapor coming here and send it back as a reflux stream that you already know in unit 5. So when we do this condensation, since glycol is heavier, it has higher boiling point, is the glycol that goes to the liquid phase first. Okay, so we can do some separation here as well. When we condense this mixture that has glycol and water, since glycol is heavier than water, so glycol goes to the liquid phase first. So we can have even the more pure water or vapor water extracted here. So the temperature at the top of the column, okay, is also an important parameter. It means the operation of this condenser, the heat duty of this condenser is also important. If we keep the temperature high at the top of the column, at the top of this column here in this part, so there will be more glycol that goes to the vapor phase. So we will lose more glycol. So if we keep the temperature here very high, we can lose more glycol. There will be more glycol that goes to this vapor phase. So it's very important to keep this temperature also in the certain range. So don't forget that the boiling point of water is 212 Fahrenheit. The boiling point of glycol that we also showed with TEG is 3-ethylene glycol is 546. The recommended temperature at the top of the column is 225, a little bit above the boiling point of water. Okay, little bit above the boiling point of water to make sure that we will have water in the vapor phase. But if we increase more this temperature, if we increase this temperature more than this value, there is a chance that we will also vaporize the glycol. So if this temperature goes to something like 250 or even above, there is a high chance to lose glycol. If we decrease that temperature to a very low value, we can condense more water here. Okay, if we decrease this temperature to very, very low value, we can decrease this temperature, we can condense more water, and we can send more water to this column. Okay, this water has to be again separated in the reboiler, so it means we will need more heat duty in the reboiler. So the temperature at the top of the column and the bottom of the column, both of them has to be in the center certain range. This figure shows you, like how these parameters are interrelated. As I say, you don't need to memorize this photo. It's just for your information to show what's the trend when we increase something, what will happen to another parameter. Okay, so for the design in the contactor, it means design for me for now, it means the diameter of the column, the absorption column, diameter of absorption column, that I have my wet gas, I have lean glycol, then I have dry gas, I have rich glycol. So this is my wet gas, this is dry gas, lean glycol, lean glycol, I show it with this TEG, and here I have rich glycol, 380 glycol. Okay, so wet gas, dry gas, lean glycol, rich glycol. So the diameter of this column is important parameter that we can, this is the diameter, and we can use this equation to find this diameter. So the definition of each of these parameters is given here. For now, I don't want you to use this equation to do any calculation. If there is anything needed to be done by using this equation, I will let you know. It's similar, very similar to many other equations that we had in designing the line heater, like treater heater and so on. This, okay, for the, this size is important. For the heat duty of reboiler, which is another design parameter, we will use this table most of the time to find the heat duty of reboiler. Okay, so as I said, the amount of the circulation rate of glycol is an important parameter, and that will affect the heat duty of reboiler. As I said, it can be something between 2 to 7. Okay, something between 3.5 is a normal operation. So this is the amount of the gallon of glycol that is needed to remove each pound of water. All right. So based on this circulation rate of glycol, we go find our heat duty of reboiler. Okay, that based on this figure, let's say for the circulation rate of 3 to 3.5. The heat duty is something 862 to 805. Okay, this is one example of how we use that equation. As I said, for now, no need to do any calculation here. If there is any need, I will explain. And also I will explain how to use those numbers in that equation, how to do the calculations. For now, no need to be worried about this part. Okay, so far I talk about the absorption process that we use glycol to remove water. For dehydration, we can have also solid bed dehydration. Instead of absorption, now we will have adsorption. And instead of glycol, now we use a solid particle. Okay, so this solid particles or solid bed is usually, for this process, dehydration of natural gas, is silica gel or alumina gel, alumina bed. What does it do? This is like activated carbon, as I said, that we have our natural gas that, let's say, that has methane and water. So this bed, solid bed, which is silica gel or alumina, it will only adsorb water and it doesn't care about the natural gas. It only absorbs the water, and in this way we will separate. So this figure shows like kind of configuration of this type of bed. It's adsorption bed. So you will send your wet gas, which is that has a big amount of water. So it goes through the column. In the column has it has an operating temperature, usually low temperature. Both adsorption and absorption, they are more efficient at higher pressure and lower temperature. So once this gas goes to the column, there is a zone that it will be saturated, and then it will start to be removed from this bed, solid beds, and then it will leave the column that free of water or with a little bit amount of water. Okay, so what will happen? The molecule of waters will be held on the surface of the solid. It will be trapped on the surface of top solid, and then after all the solid particles that are saturated with water, they cannot get and absorb more water. We have to stop the column. We have to use a hot gas, let's say hot inert gas like nitrogen. We send it to the column, and it vaporizes the water from that gas. It will be vaporized and will be collected in another column. So I will show you the configuration in the next slide. So as I said, if we increase the temperature, absorption, they are showing better performance at lower temperature. If we increase the temperature, it means we will decrease the adsorption efficiency. Okay, and for pressure, if we increase the pressure, we will have better adsorption. So adsorption is better at low temperature and higher pressure. This is the adsorption. In natural gas industry, solid desiccant. The solid desiccant means the solid particles, which is usually silica gel and aluminium. In natural gas, they are used to remove vapor water from gas stream, that I already explained. Okay, so you might ask me, when I use such a solid bed, when I use a glycol absorption process, or when I use even, I can even compress my gas. This is what happening in LPG or LNG. So I can compress and cool my gas and convert it and separate the water. So this figure is a very nice and important figure. So it's very important, try to understand it, that it shows, depending to the amount of water in the gas and the dew point of the gas, which process is more preferred. So you can see, when we are at almost very low dew point and have kind of average water content, we go low, almost low dew point and average water content, we use this solid bed. When we are at kind of high dew point and little bit higher water content, we go with this process, with the glycol process. And if we are dealing with a gas that has a very high amount of high dew point and high water content, in that case we will compress and cool the gas to separate the water. So this is a very important and nice figure that shows you what's the criteria to choose each of these processes based on the water content of the gas and dew point. We have a few more slides, maybe six slides, then we are done with this unit. It's a very short unit and not difficult at all, very straightforward. So I hope you are enjoying it so far. Now, okay, so the adsorbent that we choose, the solid particles that we use, that I said is usually silica gel and aluminium particles. So it has to have some specific properties. Those are the following, those are the properties that we need to have. Okay, this is kind of how an adsorber column looks like. So we use small particles in the middle and large particles at the top and bottom part. This is just something for your information. I'm not gonna go through the detail of this, but this is just some additional information that you need to you can see. So those are here, those are not nuts, okay? Those are not, I don't know, like nuts or even like white chocolate or something like that we use for cooking, all right? So those are solid particles. Those are the adsorbents, silica gel or aluminum particles. This is how these particles they look like. They can be very small size. They can be even cylindrical size. So they have, so as I said, those are the solid particles. They should have high adsorption capacity. They should be able to absorb a big amount of water. Then they should have microporous structure. They should have free space inside them. Okay, they should have porous structure so they can afford a big amount of water to keep inside them. And they have to be regenerated easily and economically. I will explain in the next slide what does it mean regeneration of these solid particles. The adsorption should be fast. They should have a fast adsorption kinetic. They shouldn't create a big amount of pressure drop. They should have a cyclic stability. I will show you what does it mean cyclic stability. Cyclic means because like we can use the column for both adsorption and regeneration. Okay, because we cannot move the solid particles. We keep the solid particles there. Once we send the natural gas, water will be removed, and after that we stop natural gas and we send the stripping gas to remove water. You will see in the next slide. So, and also they should have, their structure should be stable. A stable structure means they shouldn't swell or shrink. They shouldn't get bigger or smaller. They should have always stay in their stable size, fixed size. Okay, so in the next few slides, I'm gonna talk about some of the main components of this adsorption process. We need first we need an inlet gas separator to separate some of the water or impurities from the gas. We need at least two or more adsorption towers that are connected to each other and filled with adsorbent, desiccant. We need a high temperature heater that can provide a hot regeneration gas for us. This high regeneration gas will be in contact with the solid particles, and they will remove the water and reactivate the solid particles for us. A regeneration gas cooler to condense water. Okay, so after the regeneration gas, I will explain it in the next slides. Once we have an adsorption column. We send our wet gas to the column, so it's a bed of solid. I have my wet gas goes to the column, and then I have dry gas. Okay, dry gas. Once I continue this process, okay, I will continue this process until the solid absorb a big amount of water and is not able to absorb more water. So it will be saturated with water. So what I have to do, I have to stop the natural gas stream, and I have to send another gas, which is a hot gas. Okay, I have to send a hot gas. This hot gas, what does it do? It will vaporize the water from the solid phase. This hot gas will vaporize, will remove the water from the solid phase. So this hot gas, now it's a gas, let's say it can be nitrogen that has a big amount of water. So we have to send it to the cooler, that in the cooler we can condense the water, remove the water, and regenerate, and use this gas again, goes to the regeneration, to regenerate the solid particles, to remove the water. Okay, so this natural gas, this stripping gas that is used to remove the water from the solid particles, when it goes to this column, it should be hot. So we need a heater to hot it after this cooler. Okay, so that's why we need a heater, we need a cooler. Okay, those are the components that we need. And a regeneration gas separator to remove the condensed water from the so like we need a cooler here and also a separator to separate the water from the regenerator gas. And we also for sure need some manifolds, piping, control valve, control system, to provide us with the direction of the flow that we need. Sometimes we have to switch from adsorption to the adsorption process to regeneration process. So like those are the control system switching valves that they do it for us. So this figure shows, let me show if I have, this figure shows kind of the main components that we need in such a process. As I said, we have always two columns connected to each other. Okay, so we use once one of the column as an adsorption process. Okay, so let me explain a little bit here because it's very important. So I have my natural gas, okay, that is coming from separator. I have a separator that separates the natural gas is coming from reservoir. I separate some of the water, some impurities, some other impurities from this natural gas, and then I will send it to adsorption, that I have this solid particles. So my natural gas comes to this adsorber and it will be dehydrated gas. Okay, and it will be dry gas that we will send it to the downstream process. After a while, let's say after a few hours, depending to the size, let's say after a few hours, these solid particles are saturated with water because they remove the water from this natural gas, because we have dehydration this separator is used to remove a little bit of water. But after the separator, the natural gas has still a big amount of water that we have to remove it. So we will send it to this column. So once we send it to this column, here we will have a dry gas, and after a few hours, these solid particles they will be saturated with water. They are not able to absorb more water. So what we will do, we will close this valve. We send this natural gas to this column. So it will start being absorbed in this column, and we close this valve. What we will do, we will send the regenerator gas, which is a hot gas coming from heater. So this regenerator gas can be, let's say, nitrogen. It can be inert gas, it can be nitrogen, air, something like that. So what it does is at high temperature, it goes to the column and it will remove is a hot gas. It will remove all the water from this solid particles, and then it will be going to a cooler and separator that we remove the water, and we use this gas again for regeneration. So, and we will do this until all the water is removed and the solid particles is activated and is ready to absorb water. So then after that, we close this valve and we open this valve and we send again our natural gas to be dehydrated, and this column works for a few hours, and by the time that column is working, this column is now saturated because we send natural gas here when we were regenerating this. So now we again use the dry gas here to regenerate this column. Okay, the same process that we had here, we will use the same process here. So we will make this activated. By the time that is activated, this will be saturated, then we will switch to this one. So this cycle will continue, you know, like all the time, 24 hours, 7 days per week, and they will together simultaneously. Once this will be used as the adsorbent, this as a regenerator, and sometimes it will be regenerator, and this will be adsorbent. Okay, this is how this unit is working. Okay, so we saw it. Okay, how this column they work. Okay, each bed is automatically switch. Okay, let me erase this. Okay, so each of these beds, the two beds that are in parallel, they will be switched between adsorption and regeneration mode. This is one important piece of information about this. The flows are automatically switched between two columns for the optimized performance, and switching frequency is really depends to the required dew point, how much water we want to be removed, how much the type of the solid particles that we have. The switching frequency between these two columns, it really depends to some parameters like the dew point requested, the type of the solid particles that is used. And it can be time-based. Let's say after few hours, I will switch between adsorption and regeneration, or it can be dew point. I will measure the amount of water or dew point that I have at the outlet of my dry gas, and then I will see, you know, if it's a required dew point, I will stop. If not, I will continue. Then, okay, just a few more slides to finish this this part. Okay, for the adsorption mode, I already explained this, but I will repeat here. So in the adsorption mode, what I have, my feed gas to the top of it goes to the dehydration bed, and it goes down. Okay, it can be a molecular sieve descent. Molecular sieve, it means like the bed. So I have my bed. The adsorption gas will be introduced. It can be from bottom to the top or top to the bottom, but top to the bottom is more common. So my wet gas goes to the top of the column, and it will be moved downward to the inside this bed, and the water will be removed. At the end, I have a dry gas. The dry gas then exits at the bottom of the unit and is ready. Okay, and it goes to the downstream process. In the regeneration mode, what I have, as I said, I will stop this valve and I send my natural gas to another column, but I will have a hot gas here. Okay, I will send a hot gas. So the bed is first depressurized. As I said, the adsorption is better at high pressure. So the deadsorption or regeneration is better to be done at lower pressure. So I will depressurize this bed first, and then I have to heat it. I can use some product gas or some other gas, hot gas, and I heat this bed. Once I heat, I increase the temperature and I remove water from this bed. So the water will be removed. If we really need a big amount of heat to be provided, so we can use electrical heater or furnace. And then once we remove most of the water, so now the bed is dry and is ready to be used as adsorption mode. So, but it's hot. Okay, first of all, we have to cool it down. So we can use some cooled gas to cool it down, and then again we repressurize it, we increase the pressure, and we make it ready, we make it cold and pressurized, low temperature and high pressure, and it will be ready to be used as a for adsorption process. Okay, there are some concerns about the temperature, pressure, and like what's the range of this parameter. I'm gonna talk a little bit about them now. So the adsorption process is very, very sensitive to temperature. Temperature is the most important parameter in this process. The temperature of incoming gas is very important. As I said, for adsorption, we prefer to have lower temperature. So if this temperature increases, our efficiency decreases remarkably. Okay, the temperature of the hot regeneration gas is usually between 450 to 600 Fahrenheit. For the cooling gas that we use at the end to cool and pressurize the column, so it depends. For that cool gas, we can use wet gas or dry gas. Okay, we can use it. So for the wet gas, we cool the bed, because after the regeneration, the bed temperature is this much, is between 450 to 600. So we have to decrease the temperature, because otherwise the adsorption efficiency will decrease. We need to cool down the bed. You have to decrease the temperature of the bed. So we can use wet gas or dry gas, cold wet gas or cold dry gas to do this job, to cool down the column. So if we are using the wet gas, we can, once the temperature reach from this temperature to 250, that's okay for us. Okay, as I said, if we go to very low temperature, some of this vapor that is in this wet gas can be condensed and it can remain on the bed. So we don't need to go to very low temperature. So this is okay for us. If we are using dry gas, we have more freedom. We will cool down the column. Let's say we cool down a little bit. Like with the temperature difference of 10 to 20 Fahrenheit of the incoming gas. Let's say the incoming gas is at 200, so we cool it down up to, let's say, 190, 180, something like that, a little bit below the temperature of incoming gas. So the pressure, as I said, adsorption works at higher temperature, works better at higher pressure. So if we decrease the pressure, we will decrease the efficiency of adsorption. This is another point. So for pressure, better to keep it up and temperature low. Okay, the cycling time, the switching time between regeneration, adsorption. So this is also depends to how much what's the dew point, or what's the degree of adsorption that we want, and also it depends to the age of my solid particle, desiccants or solid particles. If my solid particles are old, okay, so they need maybe more cycling time. Okay, so if they are fresh, they need less cycling time, and okay. So that's also, yeah. Okay, so it means, okay, like I don't know what I said, but in general, cycling time means how longer I can use the solid particles. If they are new particles, they are young particles, so we can use them for a longer time. There will be longer cycle time. If they are aged, if they are old, we have a shortened cycle time. We need to use them the shortened time, because they don't have, their capacity won't be that much to use them for a long time. For the gas velocity in the column, for the gas velocity, so okay, the gas velocity also will have an effect, okay, if the if the gas velocity decrease, okay, the capacity, the ability of the solid particles to dehydrate the gas increases, okay. So during the drying cycle, during the adsorption, if we have less gas velocity, it means we have higher residence time, and the gas will be in more contact with the solid particles, and then the water, there will be more water that will be separated. So it's better to work at minimum gas velocity for the full use of solid particles. So how to minimize the gas velocity? We know that we have volumetric flow rate, which is velocity times area, or the diameter of column. So this is constant, this is fixed, okay. This is fixed. If I decrease the velocity, minimum velocity, I have to increase the area. Increasing the area means increasing the diameter of the column. So if you use a bigger diameter of column, okay, so the chance that you will have non-uniformity is more. So it means your gas won't be uniformly distributed across your column diameter or cross-sectional area. So you will have, let's say, more gas here than here. There is channeling, there is maldistribution or maldistribution of your gas, okay, in the column. So which is not good. So there is, as I said, it's better to work at minimum velocity, but we cannot decrease the velocity to a very, very low value. There is always some other consideration. For the pressure drop, as I said, pressure drop can also affect, pressure drop can affect the pumping, the compression system, which is not good for our process. A maximum pressure drop of 5 psi is kind of allowed. Pressure drop more than 8 psi is not recommended because it will decrease the efficiency of column. And last slide here is about some other design consideration. We know that for the column we have diameter, we have height, okay, or we show it with L. So L to D ratio, the ratio of height to diameter, is also important parameter, and more than 2.5 is desirable. If we have L to D more than 2.5 is desirable. Very low ratio, like 1/1, it means L equal to D, is sometimes is used, okay, but in that case again, since the diameter is comparing, like in that case your column is something like that. It's like, let me show, it's something like that, okay. Diameter is almost the same as D, okay. So in this case, again, you will have a maldistribution or your non-uniform flow. Channeling, okay, channeling that is happening because of the channeling means your gas goes through some part of the bed and it doesn't even see or even touch the some other part of the bed, okay. So that's not good. It goes only in center channel, not in whole cross section of column. That means when we have this kind of non-uniform distribution or channeling, there will be inadequate contact between the gas and the solid particles that result in lower efficiency of column. And also the moisture content of the gas, okay, the gas that is coming to the column for dehydration, how much water it has. So this is also important parameter that can that will affect the determine that determine the size of the column and the type of the solid bed that we can use. But in general, most of the gas that is coming to the dehydration is already saturated with water, so we don't have a lot of room to play with this because it's coming from upstream process, the upstream unit that is usually saturated with water, so we cannot really vary this or play with this. So that was all about unit 7. I hope you enjoy it.